My name is Jinghui Qin. I work at SharkNet as a HPC analyst cited at Western University. Previously, I have provided an introduction to scalable computing with Dask in Python. We talked about how Dask can help to speed up your Python code execution by parallelizing some of the operations and to handle larger than memory dataset by partitioning them into smaller chunks. The processing of those chunks of data can make use of the multiple cores on your computer or distributed to a cluster of multiple machines. We have also talked that for distributed execution crossing multiple machines, a centralized task scheduler with multiple worker processes are required to be deployed in advance on each of the machines on a cluster to work together to handle the task executions. So Dask also provides convenient APIs for data collection that can operate in parallel on datasets that do not fit into the memory of a single machine. So here is the outline of the introduction. Previously, we have covered parallelizing code with Dask delayed interface. We also talked about how to choose a scheduler based on what kind of workload you have. For Dask API for data collections, we have covered the Dask Array API for scaling NumPy array. So in this webinar, we will continue and introduce the Dask dataframe API for scaling Pandas dataframe. It can be helpful in situations where Pandas is needed. However, datasets do not fit into the memory on a single machine. For machine learning applications usually involve heavy computations. Considering a scalable machine learning, Dask-ML has resources for parallel and distributed machine learning. We will go through some examples of using cyclelearn with joblib and Dask-ML for parallel and distributed machine learning. For references, some contents and examples that I used here are from the online documentation and the tutorials available on Dask homepage. If you would like to learn more in detail, you can just go there, check out. For details about my previous webinar, the video record is available at SharkNet YouTube channel at youtube.sharknet.ca. You can go there, find out if you're interested. Okay, let's get started. Dask dataframe API is for parallel operations on Pandas dataframe. Pandas is an open source library for data analysis in Python. It provides easy to use data structure and tools for making importing and analyzing structural data much easier. Dataframe is the most commonly used object in Pandas. It is a two-dimensional labeled data structure with columns in different data types. You can think of it like a spreadsheet or a table from a relational database. So in this notebook, we will go through some simple examples to see how to parallelize data frame computation with Dask in Python. Some sample data set we used here is a collection of 10 years of historical data for flight out of New York City area. The data was originally from U.S. Bureau of Transportation Statistics, but has already been prepared for practices. So let's first take a look at what I have and try some functions of using Pandas data frame to analyze the data. As you can see here, I have a directory called data with a subfolder called NYC flight. So there are total 10 CSV files included here. So each is for the collection of flights data for one particular year. So there are total data for 10 years. The first function we would like to try is the Pandas read CSV function. It is for loading data into a data frame from a CSV file. So let's try load the data from the first CSV file. That's 1990.csv. So we can call this a head method to take a look the first 5 records in this data frame. As you can see, it represented here as a table. There are total like 23 columns, and each column has a name and with the data in different data types. The first couple of columns recorded the flight date and the time. Here, just departure time, scheduled departure time, arrival time, scheduled arrival time. All the way here is they also record the departure delay time and the originating airport. Okay, so if you would like to check a total number of records in this data frame, you can use this len function on this data frame. There are total 270,000 records in this data frame. You can also check the schema of this data frame by checking the D types attribute. Okay. So there is a commonly used method called unique, can be applied on any particular column in a data frame to get unique value of that column. So for example, here, if you would like to know what originating airport are recorded in this data frame, you just get the origin column and then call this unique method. So as you can see, there are total 3 different airport recorded in this data frame. Another commonly used function in data frame is the group by function. It is for splitting the data frame into groups based on some criteria. For example, if you would like to get average departure delay time per airport for 1 year, the first thing you would like to do is call this group by method on this data frame based on the value in the column origin. In that way, the data frame is going to split into 3 groups because we know there are 3 different values in that column. Then you get departure delay column, apply this mean method to calculate the mean departure delay time for each airport. See. Yeah, now you see these are the average departure delay time per airport for that year. So it's helpful and easy to use. Now the question is, what's the average departure delay time per origin airport for all year, since we just calculate the result from 1 year? We have total 10 years of data collected. The first straightforward solution is to write a sequential code with a for loop, right? Because we know how to get the result from single file. Then before the for loop, you would like to first get the list of file names. You can use this glob module to get the list of file names. Here is the loop. Before the loop, you will need to define 2 empty list sums and counts for storing those intermediate results you calculate from each individual file. So inside this loop, you read file like 1 by 1, right? So load the data using this read CSV and load it into a data frame, and then apply this group by method based on the origin column to split into 3 groups. And then you get the departure delay column, calculate the total number total departure delay time, and also call this count method to get the total number of departure delayed flights. And then you append this total and count to sums and counts. Then after you loop through each individual files, you calculate the total departure delay time by sum all the sums and also sum all the delayed flights to get the average. We run this code. As you can see, we also measured the time for execution this block of code. It took about 4 seconds. We get the average departure delay for the entire 10 years. Okay, that's for a sequential code using a single process or single core. Now the second solution here, we like to try to parallelize the loop in the sequential code with task delay. We have tried this before in our previous webinar when we introduced the task delayed interface. To parallelize some of the operations in this sequential code, we need to do some changes. The first thing you would like to do is to import this delayed interface from Dask package. Yeah, here just the copy of the sequential code. Okay, inside this loop, instead of loading data from the CSV file immediately, we like to delay this operation, and this will give you a delayed object, df. Then any operation applied on a delayed object will return you another delayed object automatically. So therefore, here by origin and total and count, they will all be delayed object. So here just append a delayed object to sums and also append this delayed count to this counts. Then outside the loop, instead of calculate the summation on the sums, we like delay this calculation as well. So if we run this code, as you can see, it returned the right way without giving you the exactly result for the mean. It just say it's delayed. So here mean is a delayed object. It represents some computation that hasn't yet been evaluated. We need to explicitly to call this compute method to get the result. As you can see, the runtime has been reduced almost half of the previous one, right? So when we call compute method, it triggers the default Dask scheduler, which runs at backend to compute those tasks in parallel using available cores on your computer. Since the mean is a delayed object here, you can use this visualize method to take a look at what kind of a task has been included in this delayed object. As you can see here is represented as a task graph. We read from the bottom, they were all like, you have total 10 files to read, and then you call the group by on each of them, then gather some intermediate result, then reduce to the final average. So these calculations, they are relatively independent from each other. Dask scheduler takes care of the parallelism of using available resources on your computer to get the evaluation. So this is for using Dask delayed interface for doing parallelize here. So in this solution, we like to use a Dask dataframe to automatically build similar CPU computations on a common case of dataframe. Dask dataframe look like a Pandas dataframe, but with lazy evaluation. which is a similar idea of Dask delay that you have seen in solution 2. Rather than write a for loop, we let Dask data frame construct the computation in parallel. Let's first take a look how Dask load the data into Dask data frame. Different from Pandas loading data into a data frame by reading a single input CSV file, Dask data frame read CSV can take a string as a pattern for multiple file names, like here, and then build parallel computations on all of the data at once. So here is how you're going to do in using Dask data frame read CSV. So let's run this to see what you have here. Okay, as you can see, it says it's delayed with total 30 tasks here, and also mentioned here there are 10 partitions because we have 10 files. We have a column name and then the data type for each column. However, you didn't see any actual values in this data frame here. So what just happened here is that unlike Pandas read CSV, which reads the entire file before parsing the data type, Dask data frame read CSV only reads part of the data from the beginning of the first file to parse the data type and the column names. Then these data types are then enforced for the rest, assuming that all data has already been prepared in same data schema. But still, you can use checking the schema of the data of this data frame, similar as before. Use checking the D types to get the schema of this data frame, and also you can use the head method to get the first 5 records in this data frame, which is similar as Pandas. And also try this length function on this data frame to get total number of records. As you can see here, the total records included in this data frame is 2.6 million records. That's for the entire 10 years. So now to calculate the departure delay time, average departure delay for all airport. For each airport for 10 years, you just write the similar code as you would do in Pandas when you're dealing with a single file. So just call this group by on the origin column and then get this departure delay. Remember that Dask data frame object is the same as the previous Dask array object. They're all delayed object. You need to call this compute method explicitly to get the evaluation. So yeah, the time was still less than solution 1, a little bit more than solution 2. But you get the result, and the interface is clean and easy to use. Okay. Since min is a delayed object, you also can call this a visualization. Visualize this graph to see. Yeah, it's similar to solution 2, a little bit different, because the Dask data frame, they organize such a graph and taking care of the parallelism for you. So another advantage of using Dask data frame, you can easily calculate some, for example here, maximum departure delay time for each airport. You just call max or standard deviation or any other aggregated value, the similar way you would do on a single file calculation when using Pandas data frame. But remember to put compute at the end to trigger the evaluation. Yeah, so you don't have to write like a for loop. So here is a quick summary. So in sequential code with just Panda, you need to loop over each individual file, find the individual calculation, and then at the end you calculate the final result. With task delay, you still have to think about the loops, those intermediate results, and then the final reduction. But with the Dask data frame, you can just write a Pandas-like code, read multiple files at once, then large data set are partitioned into smaller data frames. Then operation in parallel have been implemented for you. Okay. So here is a bit more information about Dask data frame. It has a blocked algorithm implemented on dataframe object to mimic Pandas API. A large Pandas data frame are partitioned row-wisely to form multiple smaller data frames. These smaller data frames could be on a disk of a single machine or multiple machines. That allows to have dataset size larger than the memory. And each computation on a Dask data frame are parallelized on smaller data frames, which is triggered by calling the compute method that takes care of the potential parallelism and the memory constraints. So Dask data frame provides a subset of Pandas API with a parallelized operation implemented. So here just some commonly used functions from Pandas API that are also available in Dask data frame. So the interface is familiar and convenient to use, but the operations are parallel on smaller data frame and can also be distributed to a cluster for a distributed execution if you have a distributed Dask scheduler deployed in advance. Yeah, we have introduced that in our previous webinar, right? So if you like to see the full Dask data frame API, you can follow this link to check out. Here are some advices. Dask data frame may not be the best choice in some situations. If your dataset fits perfectly fine into the memory of your computer, then you may just using Pandas. If you need functions that are not implemented in Dask data frame, then consider Dask delay might be a better choice for you. You can implement your customized function. Yeah, that has more flexibility. By default, Dask data frame uses multi-threaded scheduler. However, Pandas workload might be more GIL bound than NumPy. GIL stands for Global Interpreter Lock, which is a mechanism enforced in Python. That means Pandas workload might be more relying on a Python interpreter. With the GIL mechanism, it only allows one thread at a time calling a Python interpreter in one process. So multi-core speedup are not as significant for Dask data frame as they are for Dask array on a single machine. But this is changing as the Pandas development team is actively working on releasing the GIL. Dask data frame is built on top of Pandas data frame. If Pandas become less reliant on GIL, then Dask performance will be improved as well. If you would like to learn more about the Dask data frame, here is the documentation and more example. You can go there, check it out. Okay, let's take a look at machine learning. So machine learning become one of the active area these days. Machine learning itself is not new. What makes the application and research in machine learning become so active? I think part of the reason is that nowadays more and more data are generated and can be collected, for example, from those mobile devices, social network, to all those online businesses. People and business can benefit from machine learning technique to learn and get insights from those data. For example, to make more accurate prediction for future, or provide some valuable recommendation in making decisions. Machine learning usually has heavy computations, and Dask-ML has resources for parallel and distributed machine learning. In this notebook, we will go through some example of using cyclelearn with joblib and Dask-ML for parallel and distributed machine learning. But be aware that cyclelearn, deep learning of using neural network is out of the scope of cyclelearn. So cyclelearn is an open source package for machine learning in Python. It is built on top of NumPy, SciPy, and Matplotlib, and provide libraries and tools for predictive data analysis. For example, for models in classification, regression, and clustering, and etc. And also tools for pre-processing and parameter tuning and model selection. Yeah. So deep learning of using neural network is out of scope of scikit-learn. If we skip the initial pre-processing for preparing the data, scikit-learn provides a consistent API for machine learning. Here is a typical machine learning workflow in using scikit-learn. First, you choose a model by creating an instance of your selected estimator, either for regression problem or classification problem. Then you train the model by calling the fit method on some training data to train the estimator. Then you evaluate the model by using that trained estimator to make predictions on some new samples to inspect some attribute, for example, those prediction accuracy score. To improve the prediction performance, the last step you would do is for some hyperparameter tuning to find the optimal parameters for the best prediction score. Right? So the heavy workload usually involved in step 2 and step 4. For step 2, the computation workload more likely related to the dataset size and the complexity of your selected model. And in step 4, for tuning the parameter, the computation workload largely depends on the parameter grid size and how many fold of cross-validation you would like to apply. We will see examples shortly for the demonstration of this workflow. So Dask-ML has resources for scaling machine learning. The general solution in Dask-ML to scale machine learning fall into 3 categories. The first category is to parallelize scikit-learn directly. And the second category is to re-implement some scalable algorithm using Dask array. And the third category is to partner with some other distributed library, because some machine learning library already provide a distributed solution. Okay. So for the first category, to parallelize the cyclelearn directly, because the cyclelearn already provide the parallel computation with job-lib module on a single machine. We'll see example for this. Dask-ML extends such parallelism to a cluster without significantly changing your code. We will see example for this as well. So this works well for medium-sized dataset, but with large computation. For example, you have a large space of parameters searching for the hyperparameter tuning. So very typical example, like a code pieces here. You import such a client module from Dask distribute package, and to Dask-ML extend this parallelism to a cluster. So first thing you will need to do is create a client instance to connect to a Dask scheduler if you have such a distributed scheduler deployed on a cluster in advance. Then before your regular cyclelearn code, you add this with job-lib parallel backend Dask to make use of the resources on the Dask cluster. So we'll see this shortly. Yeah, to re-implement a scalable algorithm with Dask array, because some algorithms are easy to write as NumPy algorithm. For example, those linear model and pre-processing tools. Just replace NumPy array with Dask array, then you can achieve a scalable algorithm. This is helpful for handling large memory dataset. Here, just some code pieces. For example, if you would like to use those categorizer and dummy encoder, those pre-processing tools, instead of import them from the scikit-learn package, you import them from Dask-ML pre-processing. And also, if you would like to use any linear module like a logistic regression, you import them from Dask-ML linear model. The rest of the code is the same as what you would do in using scikit-learn. Okay, this is for this part. Yeah, some machine learning library, as I mentioned, like XGBoost and TensorFlow for deep learning, they already have distributed solution. Dask-ML can deploy distributed XGBoost or TensorFlow on a Dask cluster, then hand data over. Such that two distributed services can operate together on the same data, which benefit from Dask in handling large data set. But this part is still in rapid change with active development. So if you would like to learn more, here are the documentation. You can go there, find out. Okay, let's see an example. Here is the example we like to demonstrate the workflow of using scikit-learn and how to scale the computation workload on a single machine using multiple cores and on a cluster of multiple machines. Because scikit-learn has some random sample generator for building artificial data set. So here, we like to use this make classification function to generate a classification data set for classification problem. It creates a pair of random array, one for featured data X, and the other is for the target or labeled data Y. So for simplicity, here we just create a total 10,000 samples, and the featured data only have like 4 features. For the labeled data, we here just have 2 different classes. We can take a look at what's included in this first 8 samples. As you can see, each sample has 4 columns for 4 different features. And for the labeled data, first 8 sample labeled data here, as you can see, only have value 0 and 1 because we only have like 2 classes. Then, yeah. Okay. The next is to fit the sample dataset with support a vector classifier. So first thing we need to import this package from cyclelearn. Then we need to create an instance of a selected estimator. So in general, each estimator has some parameter you need to provide some values when creating an instance of a selected estimator. If you don't provide any value, then some default values will be used. Here we just provide this value. So C is a penalty term in this estimator for regularization purpose. And then for each support vector classifier, you need to specify a kernel function. So here we use the RBF kernel function and some other parameter. Let's train this estimator, call this a fit method on our data. As you can see, these are the rest of the parameter we didn't give value, just default ones will be used here. And then we check the accuracy by apply this trained estimator on some new data set. For demonstration purpose here, we just apply on the same data set we used for training to check the accuracy score. So yeah, we got the score is 0.906. So remember, we have C value as 1 here. Different value will give you different trained model, actually. So those parameters are called hyperparameter. They are not like you cannot train those from your training process. So if we try using a different parameter value for C here to do the same fitting on this data set, and then we check the accuracy score. As you can see, you get the worst score here. So those value used, it does have strong impact on your model prediction performance. So how to get the optimal parameter for the best score? This is the process called Hyperparameter Tuning. There is a function called the grid search cross-validation. Is for the purpose. So for example, here you have this estimator, but you would like to try 2 different C values and 2 different kernel functions to see which combination of these parameter performs the best. So here is you define such a grid search cross-validation. Another important parameter here is CV. So here CV equal to 3. That means we're going to do a 3-fold cross-validation. So basically, for a 3-fold of cross-validation, for each candidate of those parameters, it will go through 3 rounds of fitting and validation procedure. Then average the 3 validation score as the score for that candidate. After you complete such a procedure for each candidate combination of those parameters, the optimal parameter with the best score will be returned. So let's fit this training data. So the total number of fitting here you can calculate because we have 2 parameters, each with 2 different values. So total candidate here is 4, right? 4 different combinations. And then each will go through 3 rounds. So total will be 12 fitting, right? 3 times 4. Oops. I need to run this first and then run this. See, you may also notice that here, parallel parameter n job, we didn't provide any values for that. So the default is 1. That means just using 1 core for this process. So let's see what's the runtime. Yeah, it took about 10 seconds to complete all 12 fitting. So let's see what's the best score and the best parameter. See, the parameter c equal to 10, and the kernel use RBF is the best. Score is 0.91. It's better than the first try we did using c equal to 1, right? So this is using the single core. So scikit-learn has nice single machine parallelism with job-lib. So you need to provide such n job keywords, given value. If you provide the -1 here, that means you will use all available cores on your machine, or any other number less than number of core. You can put it here to make use the specific number of cores for doing the same fitting here. Let's try to do this. So total 12 fit will use, it says 8 concurrent cores. This machine has hyper-threaded. So as you can see, the runtime just cut about half. Yeah, but still better, right, than the single core process. And then you can check the best score. Yeah, it's the same result as before. So for our clusters, Dask extends such parallelism of scikit-learn using job-lib to a cluster, but you do need a distributed Dask scheduler deployed on a cluster in advance for using that. For in your Python code, what you need to do is create a client instance to connect to the Dask scheduler, if you have such one deployed in advance. Then you can have a large parameter grid defined here. For example, we like to try 6 different C value and 3 different kernel function and 2 different options for shrinkage parameters. And then you do the similar as you would do in using scikit-learn with job-lib, but you need to specify job-lib parallel backend with Dask to make use of the resources register with that Dask scheduler. So I don't have such a scheduler deployed on cluster right now, but yeah, I do have some results that I previously run on one of Computer Canada cluster, that's Graham. So total number of fit here is because of 6 C values, 3 kernel function, and 2 shrinkage, and each will do 3 rounds of cross-validation. So total will be 108 fitting. So I can show some of the results I did before. So here, just import some packages or modules that you would like to use to connect to the Dask scheduler that I deployed on like 3 nodes. One is for the scheduler node, the other 2 are the worker node. The information about the scheduler, the address and the port number I recorded in this scheduler file. So in this way, you can connect this client to the Dask scheduler. So check the detail. As you can see, it tells you there are 2 workers with total 64 cores, and each has memory 230 gig. That's 32 core on a compute node, a very typical compute node on Graham. And then here is the code to run exactly same task that I showed you before. And then for threefold for each 36 candidate, total fitting is 108. Using 64 concurrent worker, it took like 11 seconds. The best parameter showing here give you the result. C is 10, kernel B, RBF, and the shrinkage is 2. The best score is like that. Okay, this is just to show you what you can do using a cluster. Okay. Yeah, to learn more about Dask-ML, you can go there, check the documentation, and more examples.